Hello and welcome to the video for Chapter 7.1 on the area of the region between two curves. This starts Chapter 7, which is going to focus on areas and volumes. We'll look at the areas in this section, and then we're going to do Section 2 on what's areas by cross sections, and then 7.3 deals with cylindrical shells. We'll kind of look at that and get a feel for that one, but we'll not necessarily go as in depth as we will with the area by cross sections. And then we'll move to Chapter 8, and we'll finish up the course there in Chapter 8, doing a couple sections there. But with that, let's just get started with Chapter 7. The objectives for this particular video are: 1, find the area between two curves using integration. Number 2, find the area between two intersecting curves using integration. And number 3, describe integration as an accumulation process. Right now, the focus of this video is just going to be in actually doing those three. In class, we will talk about, in terms of slicing. When we look at these, one of the things you're going to want to determine is what type of slicing, and because that's going to determine how you're going to integrate the problem. But for right now, for what we have, we're going to be looking at just finding these areas and using basic functions that you're familiar with. So let's go and take a look. In this first thing, I want you to recall that when we developed the idea of the definite integral, we defined it as a way to find the area between a curve and the x-axis over an interval from a to b. So in this case, I have right here, I have this function y equals f of x, that's right here. And we're going from a to b, and we get this region that's shaded in red, and I called it R sub 1, region 1. And when we dealt with this before, we started out doing Riemann sums, found areas using rectangles, and we made the rectangles get closer until we got the whole idea of the fundamental theorem of calculus. And what we found was that the area of region 1 would just be the definite integral from a to b of f of x dx. Well, now what we're going to do is we're going to take that definition that we have here of the idea of the definite integral being the area between the curve and the x-axis, and we're going to go and use that to help us identify how to find the area of a region, like region 2 here, which lies between the two curves. Well, the one thing you might want to remember, keep in mind, the area, the definite integral, tells me the area between the curve and the x-axis. So if I went through on this and I found the integral from a to b of f of x dx, what I'm going to end up finding is the region here, this portion here, here, and all the way down here. That is going to be what we have there. Now we just want this part that we had here between the two curves. Well, you'll notice on that if I go and take that definite integral, and then I go and subtract the integral from a to b of g of x dx. So I'm subtracting the area between this curve here and the x-axis from a to b. That will give me that area. And so when we look at that, properties of integration tells us that we can take that and we can rewrite that as the integral from a to b of f of x minus g of x dx. Now another thing you can do with this one, you want to keep in mind, because you're going to see these curves placed all over the place. It is always, f of x is always going to be the top function, and g of x is always the bottom function. Okay, and if you want to know how to go through and determine the top or the bottom, go to the top of the page, put your pencil above the region, and come down. The first one you come to is going to be the top function. The second one you come to will be the bottom function. So the area of a region between two curves, in terms of a formal definition here, if f and g are continuous on the closed interval from a to b, and g of x should be less than or equal to f of x for all x in the interval from a to b, then the area of the region bounded by the graphs of f and g and the vertical line x equals a and x equals b is the the definite integral from a to b of f of x minus g of x dx. Let's take a look at an example of this. So in this example here, I want to find the area of the region bounded by y1 equal x squared plus 1 and y2 equal to x from x equals 0 to x equals 3. So what you see here is I've made a sketch, something close to x squared plus 1 and something close to y equals x, and those are y1 and y2. And I wanted x equals 0, which is the y-axis, and x equals 3. So the region that I'm trying to find the area from is the region shaded in red. Well, in this case, again, the area is, remember, it's going to be the integral from a to b of the top function minus the bottom function, and we're integrating with respect to x. Well, in this case, my top function is x squared plus 1. My bottom function is x. A is 0, b is 3. So my area is going to be the integral from 0 to 3 of x squared plus 1 minus x dx. Now I went through and simplified that, and you can do you have the option to do that. You can choose to do it, or you can choose not to do it. I just went through and put it into that traditional descending order. So that is the integral from 0 to 3 of x squared minus x plus 1 dx. Really what I do is just find the antiderivative of each term. Well, the antiderivative of x squared is 1/3 x cubed minus 1/2 x squared plus x going from 0 to 3. At this point, I'm just evaluating the definite integral using the fundamental theorem of calculus. So I put the 3 in, so 1/3 times 3 cubed minus 1/2 times 3 squared plus 3 minus what I get when I plug 0 in, which is actually going to be 0. And so when I simplify that, I get 9 minus 9 over 2 plus 3 minus 0. And if I go and get a common denominator, combine everything, that will calculate to be 15 over 2. And so in this case, the area of my region is 15 over 2 square units. Pause the video right now if you have any questions about what I did, or to make sure you get everything written down the way you want it to. Otherwise, let's go on to our next example. In this case, I want to find the area of the region bounded by f of x equals 4 minus x squared and g of x equals x minus 2. Now notice in this case here, we haven't been told the a and b. Well, what's happening on this one is a and b happen to be the x coordinates of the intersection points that I have here and here. And so to find those, what I have to do, I'm going to set f of x equal to g of x. So I'll have 4 minus x squared equals x minus 2. And what I'm going to do is I'm going to move everything, in this case, I'm going to move everything over to the right because that will give me a positive x squared. So when I do that, I'll subtract 4 and x squared and add an x squared to both sides. So when I do that, I'll get 0 equals x squared plus x and minus 6. And so I want to solve that. I need to factor it. That will factor as x plus 3 and x minus 2. So my intersection points are going to happen when x equals negative 3 and x equals 2. So in this case, A is going to be at negative 3 right here, and B is going to be at positive 2. So I'll set that up, put the negative 3 into this spot, and I'll put the 2 up here. Now at this point, I'm going to go and simplify that expression, negative 3 to 2. 4 minus x squared minus x minus 2 will come out to be negative x squared minus x plus 6. And that's going to be dx. And so when I take the antiderivative, I'm going to get negative 1/3 x cubed minus 1/2 x squared plus 6x. And again, we're going from negative 3 to 2. So to do this, I will now go through and evaluate it using the fundamental theorem of calculus. When I put 2 in, I'm going to get negative 8 over 3 minus 4 over 2 plus 12. And I'll be subtracting, when I plug 3 in, or negative 3 in, I'm going to get a positive 9. Put in 3 squared. That was going to be minus 9 over 2. And it will be minus 18. So I'll get negative 8 thirds minus 2 plus 12 minus 9 plus 9 over 2 plus 18. And now when I go through, combine all the like terms, get a common denominator, that will come out to be 157 over 6. So the answer in this case is that that area is equal to 157 over 6 square units. The last thing I need to kind of just remind you on is the whole idea of the area as an accumulation, this integration as an accumulation process. In other words, what's happening here is that when we dealt with, by changing where we have our upper limit of integration, we're going to be adding more area to a problem. So if I had the integral from -1 to -1, I know that is one of our rules is that's going to be 0. But as I go through and I increase this, I'm going through and I make, like if I went to -1/2, I would go through and we had a rectangle. And every time as I increase this, I always added in more by increasing b. I ended up adding in more rectangles and therefore increasing my approximation for the area. And so as you go through with this, as you move over in this direction towards the right, we're going to be going through and you're going to be adding in more and more rectangles. And we just keep going. We can use whatever rectangle wherever we want it to be, but we can get to areas of more rectangles, and that's why this process is called an accumulation process. You do have to keep that in mind as we go through. Once we finish up the class and we start looking at more review problems, you'll see this same idea coming through in some of the other problems that we've dealt with as well. So with this, I will bring to a close this particular video. Again, what you need to have out of this one is just how you go about setting up a definite integral to find an area between two curves. Please be aware that whether or not the function, the graph is above or below the x-axis in this case does not really come into play when we start looking at as a region between two curves. It's really just going to be the top function minus the bottom at all times. So with that, I hope you are having a good evening, and we'll see you in our next class.